All right, welcome back to another video where I study for my JNCIE-SP exam that I'm planning to take in September. So one of the kind of biggest, most significant life events I would say occurring this year is studying for that exam. A few minor events in my life, just to kind of talk about that a little bit. I just finished my taxes and I've got a code for 20% off. So if anyone wants that code, I'll put that in the description. And then kind of with whatever extra time I have, I want to start getting into development for VR. So I've got the Unity engine here and I'm downloading some tutorials. I've already got all the basic tutorials downloaded. So I just am downloading the VR tutorial, and then when I'm done with these, I'll have that ready to go. But that's in my spare time. Right now, it's the time dedicated to work on this test I've got coming up, which is kind of one of my biggest things on the horizon. So I'm going to need to minimize that and pull up my lab again. Unfortunately, I keep that window open because I'm downloading a 3.5 gigabyte tutorial with only 10 free gigabytes of space on this laptop. But hopefully there's no issues with that. And hopefully I can ignore that and continue on with this lab. So first step. So last video, I finished configuring the lab. I did some Wireshark captures. I introduced the new command that hasn't been in any of these labs, but it's a very useful command. It's the passive command at the end of the neighbor command within a BGP neighborship configuration. And that makes it so that the BGP session is only initiated from the side without the passive keyword. And that can prevent a race condition where both devices try to establish the BGP connection, and then you need a special mechanism where one device can recognize, oh, my router ID is higher or my router ID is not as high. If it's higher, then I'm going to be the one who establishes the connection. If it's lower, then I'm going to back off and let you establish the connection. And then we saw in the Wireshark many times how this is accomplished is if it's determined that mine is lower, I'll send some extra fin packets and that'll let you know that you're the one who's going to be initiating this session. But let's just go route line for line through the documentation and finish up this exercise and make sure we've got everything in here that the lab is expecting us to have. So it looks like it's expecting us to have 1, 2, 3, 4 peering relationships. Let's do a pipe match peer. And sure enough, we've got 4 of them. Looks like nothing's bolded or anything kind of specific to look at. So I don't see anything that says to check for specifically, but we've got all 4 neighbor relationships up. All are in established. I would use BGP summary for that. And you can see they're all in established, otherwise it would tell you what state it was in besides established. So let's just enter this command one more time to kind of get used to entering it. Show BGP, and let's look at the description. So show border gateway protocol information. And then let's see what it says for neighbor. Show the BGP neighbor database. And let's see what kind of extra options we've got afterwards. Exact instance fabric. That sounds interesting. Instance logical system. Outbound route filtering information, ORF. Outbound routes queue depths by priority. So looks like I got a bad daemon or daemon, however. So I can't look at the fabric information, but hopefully that's not on the exam in any way. kind of important in my mind. I think, yeah, like curiosity is always really important. It'll help you learn more, but often you can go on red herrings, you know, false paths, and it just eats up your time, and all of a sudden you realize you didn't spend enough time in the things you actually will need to know for the context and situation you'll be in. That can be a big problem. All right, show BGP group. So we've got one group with all 4 of those connections in it, which is the, as we saw in the note above, which is the recommended way to configure them. You wouldn't have a group for each connection. The more general your groups can be, the smoother BGP will run. If you have more specific groups with a fewer number of neighborship statements in each group, you're going to have resource issues with your routing device, and you won't have those issues if you have more general groups with a large number of neighbor relationships assigned to each group. So I guess the minimum level of the kind of a good way to start is you have a group for your external peers, a group for your internal peers, and then that's pretty much it. Like having more than 5 groups, I think would be very unusual. Okay, so let's take a look at the show BGP summary. And yep, it looks like we've got 3 connections to AS22 and 1 connection to AS79, and they're all in established state. So everything looks great. All right, moving on to the next one. So now we're going to be looking at IPv6, which is going to be looked at more closely in the next topic, which is going to be IPv4 and IPv6 peering communities. But of course, that's going to be peering communities, so it might be a bit different. And this example shows how to configure external BGP, EBGP point-to-point peer sessions on logical systems with IPv6 interfaces. So it doesn't say anything about communities, so it's probably a different subject. Junos OS supports EBGP peer sessions by means of IPv6 addresses. An IPv6 peer session can be configured when an IPv6 address is specified in the neighbor statement. This example shows EUI-64 this example uses EUI-64. So this is going to be a combination of the MAC address and then I believe randomly generated bits to make an IPv6 address, to generate IPv6 addresses that are automatically applied to the interfaces. An EUI-64 address is an IPv6 address that uses the IEEE, IEEE EUI-64 format for the interface identifier portion of the address, the last 64 bits. So unfortunately, it's not going to go into detail what that format is. I think I gave a general explanation for it. This was actually a topic of many other exams, CCNA, so it's something I'm familiar with. I've seen a lot. Unfortunately, I might be a little bit, because I don't work with it every day. I really don't do a lot of IPv6 professionally. Unfortunately, right now, I'd really love to kind of have a wider breadth of things I work with, but I do have an understanding of what it is, but we'll definitely go in deeper and read an official definition of it. Alternatively, you can configure EBGP sessions using manually assigned 128-bit IPv6 addresses. If you use 128-bit link local addresses for the interfaces, you must include the local interface statement. This statement is valid only for 128-bit IPv6 link local addresses and is mandatory for configuring an IPv6 EBGP link local peer session. So, okay, so instead of using a IEEE EUI-64 auto-generated IPv6 address to form a neighborship, you can use a statically defined one, a manually assigned one, instead of the auto-generated one. And in fact, you have to include a special statement to say that it's manually defined, and it's the local interface statement. And it's only valid for those particular addresses. If it's auto-generated, if it's in the format, which we'll see later, of a auto-generated address, you can't use this knob, as Juniper likes to call it. But the thing is, if you're configuring it using link local addresses, then it's mandatory, actually. Configuring EBGP peering using link local addresses is only applicable for directly connected interfaces. There is no support for multi-hop peering. And that makes sense because of what a link local address is. It's kind of IPv6's solution for ARPs and the broadcast storm kind of problems you can get with ARP and IPv4 having to map a MAC address to a IPv4 address. With IPv6, you don't need to map those. You have link local addresses that can kind of serve that same function, but do in a way that doesn't have such severe consequences as broadcast storms. After your interfaces are up, you can use the show interfaces terse command to view the EUI-64 generated IPv6 addresses on the interfaces. You must use these generated addresses in the BGP neighbor statements. This example demonstrates the full end-to-end procedure. In this example, frame relay interface encapsulation is applied to the logical tunnel interfaces. This is a requirement because only frame relay encapsulation is supported when IPv6 addresses are configured on LT interfaces. Figure 3 shows a network with Bgp Peer Sessions. In this sample network, router R1 has 5 logical systems configured. Device E in Autonomous System 17 has BGP Peer Sessions to a group of peers called external peers. Peers A, B, and C reside in AS22. Okay, yeah, so this is just explanations about kind of a general overview of what we'll be doing more specifically. So I think I'm gonna go ahead and drop this logical system again. It's just kind of made things a bit more difficult. So hopefully by merit of doing that, I won't need to set up frame relay. It'll kind of change this, but I think that'll be really interesting to see. I'm kind of a little bit perhaps rusty with IPv6 just because I don't see it and use it every day, unfortunately, but I've definitely had a lot of training in IPv6, so just about every thing in the book really has been thrown at me, and I'm really not seeing anything new for the first time. It's just a matter of what I deal with day to day. All right, let's try to find a good explanation of this format. Looks like that one's a little bit wordy. I want one that's a little bit more congested, kind of to a lower scope of audience. So I think this one looks okay. Extended Unique Identifier, EUI, per RFC 23273. So already this is perfect. It gives me the actual unpacked version of the acronym, and then it gives me the parent, granddaddy resource of what this all means. Like this, it just in the 1, 2, 3, 4, 5, 6 words, I can tell this is just an amazing educational resource. Whereas if I go back to this one, they use it, but they don't explain what it means. And then they use it 2 more times without explaining what it means. So this is just a really bad resource. So extended unique identifier, EUI, as per RFC 2373, allows a host to assign itself a unique 64-bit IPv6 interface identifier, EUI-64. This feature is a key benefit over IPv4 as it eliminates the need of manual configuration or DHCP as in the world of IPv4. The IPv6 EUI-64 format address is obtained through the 48-bit MAC address. The MAC address is first separated into two 24 bits, with one being OUI, organizationally unique identifier, and the other being NIC, network interface card specific. The 16-bit 0xFFE is then inserted between these two 24 bits for the 64-bit EUI address. And I forget what that stands for again. Extended unique identifier, which makes sense because you're building a unique identifier, and then it's going to be extended based on the MAC address, and then based on the OUI. So it's going to be the MAC address is separated into two 24 bits. MAC address is usually 3 octets, so 8 times 3, so 20. Well, let's look at a MAC address just to be extra 100% sure. So here we go. Wikipedia is usually a good first place to look. So this looks like a great chart. So a MAC address is actually, 48 bits. So 6 octets. So 8, 16, 24, 32, 40, 48. MAC address is 48 bits. I don't know why I said it was 24 bits. I just probably couldn't get it out of my head what I just read, but it's definitely 48 bits. And then the first 3 octets are an organizationally unique identifier, OUI, and it tells you what company it was made from. So let's say you've got a Cisco device, let's say you've got a Juniper device. Each of those devices are going to have a different OUI, but let's say you have a Cisco device, you have 2 Cisco devices, and then you have 2 Juniper devices. Each of those 2 devices for each vendor are going to have the same OUI. And those will specify, you'll be able to tell if I'm just here and I do a show ARP, just from these MAC addresses here, you'll be able to tell which vendor it came from. And you can see, yep, sure enough, they're all the same. The first 3 octets, so the first 24 bits are all the same because they all came from the same vendor. And then these are going to be all unique. It's the network interface controller specific. So that's going to be even unique to the particular port that I use. Okay, so continuing to read. So this feature is a key benefit over IPv4. It eliminates the need of manual configuration. Okay, yep, read that. It's first separated into 24 bits, 2 24 bits. So let's build out a OUI for one of these. So let's take one of these MAC addresses here, and then let's build out an OUI and then see, of course, if that's what jumps out. So the MAC address is first separated into 2 24 bits. So let's do that. There we go. For the 64-bit extended unique identifier address. IEEE has chosen FFFE as a reserved value which can only appear in an extended unique identifier -64 generated from an EUI-48 MAC address. That's interesting. So extended unique identifier, that does not mean that it's an IPv6 address. It just means it's an extended unique identifier. So a MAC address is an extended unique identifier. But the way you would kind of give an extra clue as to whether it's a MAC address or a IPv6 address is you'd have this -48 is the MAC address, because MAC addresses have 48 bits. But it can be a little confusing because you can see -64, you're talking about a extended unique identifier for an IPv6 address. Well, that doesn't make sense. Are IPv6 addresses 64 bits? No, they're 128 bits. But you only need half of that to be unique, and then the rest of it can be however you would like it to be. I'm sure it'll go into more detail down there. So here's an example showing how the MAC address is used to generate extended unique identifiers. So let's see if we can take a look and do this with this one before we get to that one. Or actually, let's just see if we can do it with the example and see if we get the right answer just based on what we understand so far. So here's my 6 octets. So I'm going to need to split them. Then I'm going to need to add the FFFE. And then I thought I needed to flip a bit. I think it's the 7th bit. So this first octet is 00. So the 7th bit is going to be the 2. So I think it's going to go to 0, 2, 212, F, FFFE, B65, E10. I think that's how it's going to be, but we will definitely see. So here's the 64 bits. Okay, next the 7th. So we got this right so far. This was really easy. All you needed to do was split it in half and then add FFFE. But there's one more step to create a extended universal identifier -64 for IPv6. Next, the 7th bit from the left, or the universal -local UL bit, needs to be inverted. This bit identifies whether this interface identifier is universally or locally administered. If 0, the address is locally administered. If 1, the address is globally unique. So, which one would you want for a extended universal identifier? Well, universally, if you want to identify this one specific thing, I think obviously you want it to be globally unique. So yeah, you're going to have a 1 there. And then why is it going to be 0? Why can you reliably know that you're going to toggle it from a 0 to a 1? Why won't you get a MAC address sometimes that has that 1, and then, oh no, you toggle it to a 0 and you'd be saying that it's locally administered? It's because a MAC address is talking about a thing that's locally administered, so you're always going to have a 0 there. It is worth noticing that the OUI portion, so let's look that up again, organizationally unique identifier portion, the globally unique addresses assigned by the IEEE has always been set to 0, whereas the locally created addresses have 1 configured. Therefore, when the bit is inverted, it maintains its original scope. Global unique address is still global unique, and vice versa. The reason for inverting can be found in RFC, and then hopefully it's the one we've already got open. Nope, it's not. But I would like to read more about that because that's something that has never really clicked with me, why you've got to invert that bit. So I think this section of the RFC is kind of the ultimate resource for that. So I definitely want to go ahead, dive in and read about that. But I'll finish this first and we'll see if we got the right answer. So sure enough, the 7th bit is the 2 value. So we're going to be turning a 2 on. And you can see we've got 0, 2. Then we've got 2, 1, 2F. Then we've got FF, FFE. Then we've got B5, 6E, 1, 0. So we got the right answer. Once the above is done, we have a fully functional extended universal identifier -64 format address. Another doubt or frequently asked question is, are IPv6 devices, routers, etc. today doing anything to that universal-local bit? Currently, nothing is being done by the U/L bit 1 or 0. However, per RFC 429 2.5.1, which we got open in this other tab, we're going to read after this, the use of the universal/local bit in the modified EUI extended universal identifier, extended unique identifier -64 format identifier is to allow development of future technology that can take advantage of interface identifiers with universal scope. This may change in the future as technology evolves. So that's one of the things that they're always trying to do with these standards, is just kind of look forward to the future and kind of leave things for people to play with or work with in the future. All right, so yep, we got that right in the example. Let's go ahead and see if we can come up with an answer for this one and just save it, and then when it actually gets configured, go and check that answer. So let's start with the easy part. So it's going to be just copying whatever is above there, and then adding the FFFE. So that's Step 1 is, of course, splitting it apart. Step 2 is adding that FFFE. And then we're going to have one more step left, and that's flipping the 7th bit from the left. So from the left, we've got a nibble, because when it's in hexadecimal, it's talking about 4 bits at a time. And that nibble is worth 0. So we've got something that looks like this. Then we've got a C. So A is 10, B is 11, C is 12. So we've got another 4 bits here, but we've got it toggled so that we're representing a value of 12. So to do that, you've got to turn on the 8-bit and you've got to turn on the 4-bit. So this is what we've got in those first 7 bits. So now, in order to toggle the 7th bit, change it from a 0 to a 1, so we added a value of 2. So instead of 12, we now have 14. So CDE. So now we have an E here. Oh, and I'll do that in another steps just so we can see the work that was done. And I'll even write down what the steps were. So step 1. Step 1, split MAC in half. Step 2, insert FFFE in the middle. And then step 3, flip the 7th bit from the left. There you go. So it's just this easy 3-step process. and then we get the final answer, which I'll clean up nice and pretty so it's easy to compare to see if we got it right. There you go. So that would be nice and easy to check. We'll see now this is 64 bits, so it's gonna, sorry, it's 64 bits. So these are all groups of 8 bits. So we got 8, 16, 24, 32, 40, 48, and then we've got 56, and then another 8 is 64. So 64 bits here is what we're going to be using for our extended unique identifier. All right, so let's read that extra section about the bit toggling in the RFC, because I'm just curious to know more about that. It sounds like it's a little bit complicated about why it's always going to be a 0, and then how changing it to a 1 for 1 affects the address of the whole. That seems a little bit complicated and I'm not too familiar with. And then 2, how that might be used in the future, why that's a useful thing to do. So, interface identifiers. Interface identifiers in IPv6 unicast addresses are used to identify interfaces on a link. They are required to be unique within a subnet prefix. It is recommended that the same interface identifier not be assigned to different nodes on the link, on a link. They may also be unique over a broader scope. In some cases, an interface's identifier will be derived directly from that interface's link layer address. The same interface identifier may be used on multiple interfaces on a single node, as long as they are attached to different subnets. Note that the uniqueness of interface identifiers is independent of the uniqueness of IPv6 addresses. For example, a global unicast address may be created with a local scope interface identifier, and a link local address may be created with a universal scope interface identifier. For all unicast addresses, except for those that start with the binary value 000. Okay, well that's interesting because this one actually does start with the binary value 000. Interface IDs are required to be 64 bits long and to be constructed in modified extended universal identifier -64 format. Modified EUI-64 format based interface identifiers may have universal scope when derived from a universal token. Example, IEEE 802 48-bit MAC or IEEE EUI-64 identifiers, EUI-64, or may have local scope where a global token is not available. Example, serial links, tunnel endpoints, or where global tokens are undesirable. Example, temporary tokens for privacy. Modified EUI-64 format interface identifiers are formed by inverting the U bit, universal/local bit, in the IEEE EUI-64 terminology. When forming the interface identifier from IEEE EUI Extended Universal Identifier -64 identifiers, in the resulting modified EUI-64 format, the U bit is set to 1 to indicate universal scope. So extended universal identifiers are always going to be in universal scope. And it is set to 0 to indicate local scope. The first 3, extended unique identifiers. They're not universal. They're extended unique identifiers. It is set to 0 to indicate local scope. The first 3 octets in binary of an IEEE extended unique identifier -64, and I'm just gonna look up that description again because you can see my brain is kind of doesn't have that U word wired up properly, and it's confusing it with universal, even though it's the opposite of that. It's unique. it's an extended unique identifier. It's a method that we can use to automatically configure IPv6 host addresses. So a host address has got to be unique. Yeah, unless of course you're natting it, getting kind of more fancy. So let's continue reading. Fortunately, okay, so there's not that much left to read. The first 3 octets in binary of an IEEE extended unique identifier -64 identifier are as follows. Written in Internet Standard Bit Order, where U is the universal/local bit, and G is the individual/group bit, and C is the bits of the company ID. Appendix A, creating modified extended unique identifier /64 format interface identifiers, provides examples on the creation of modified EUI-64 format-based interface identifiers. Perfect. So this is what we need to learn here. The motivation for inverting the U bit when forming an interface identifier is to make it easy for system administrators to hand configurable non-global identifiers when hardware tokens. Oh, sorry, I misread that. So the motivation for inverting the U bit when forming an interface identifier is to make it easy for system administrators to hand configure non-global identifiers when hardware tokens are not available. This is expected to be the case for serial links and tunnel endpoints. For example, the alternative would have been for these to be of the form 0200:0:0:1, 0200:0:0:2, 3, 4, etc., instead of the much simpler 0:0:0:0:1, 0:0:0:2, 3, 4, etc. IPv6 nodes are not required to validate that interface identifiers created with modified EUI-64 tokens with the U bit set to universal are unique. The use of the universal /local bit in the modified extended unique identifier -64 format identifier is to allow development of future technology that can take advantage of the interface identifiers with universal scope. The details of forming interface identifiers are defined in the appropriate IPv6 over link specifications, such as IPv6 over Ethernet and IPv6 over FTDI. So it's always good to kind of have an eye on the RFCs. I mean, as you can see, there's a lot in here that just isn't really necessary to know. Educational resources, when you want to be educated, I think are always going to be more valuable than resources intended for a scope of, or an audience of other professionals who have already received all the education they need. But one final thing before moving on with the exercise I would like to do is just Google development of future technology that can take advantage of interface identifiers with universal scope. I mean, that seems like it would, there'd be some interesting results associated with that. So it looks like satellite systems might be able to do that. So looks like this is another RFC. Future is now. That seems unrelated. But this RFC here might be interested because it might be saying that it's going to take advantage of that scope. But yeah, here's a whole okay, well, this looks like just an explanation of the same thing that we just read. It actually looks like it's copied straight from the RFC. But yeah, I mean, there's going to be a lot of, if anyone who's watching this channel has followed Starlink. Yeah, so SpaceX is developing a low latency satellite constellation network. So they might be either taking advantage of that bit and using IPv6 or developing their own systems. But in either case, you know, having a sense of what's coming down the line in the future is really exciting. I think there's always, I mean, this stuff was developed to allow for future use. So you know, not to say that they're going to be using IPv6 addressing for all their satellites. They'll probably use whatever makes the most sense for them to use. But they're definitely going to need to be making decisions, like as was made in that IPv6 standard, where they have to assign meaning to their bits and they've got to choose how many bits they want to use. You know, it's got to be a number that makes sense with the ultimate number of satellites they're going to use, and it's got to be a number that allows for enough unique identifiers. So lots of really interesting things, and not that you can ever, I mean, not that it's well, let's take a look. SpaceX, Starlink, and let's type in jobs, because I remember one thing I like to do is just kind of poke around and see like what's interesting out there, what kind of jobs are being sought after, because that's kind of another good way to see like the future, like, oh, they're thinking of bringing on someone that's going to design a whole, you know, satellite constellation network. Well, you might have kind of an insight into what's going to happen before anything actually happens. So I remember a while ago they were actually looking for a network architect for wireless technologies, but they must have gotten that person, and the job description was really kind of telling, because it was saying they wanted to design a lot of their own protocols and really do a lot of advanced things that are not being done, I think, in more traditional companies. So really fascinating, interesting stuff coming out of SpaceX right now, especially with network engineering. But unfortunately, there's going to be a lot of competition for these jobs. So unless you've got master's, PhD, you know, multiple IEs, multiple JNCIEs, I just don't think it's like a super realistic thing. But you can always, I mean, just applying, putting your resume there, it's always good to have your resume up to date and to kind of know that you kind of prepare yourself to even though you won't necessarily get this one. I mean, they're even asking right in the application what your GPA is. So if your doctorate level GPA is too low, I don't know if you got a shot, but it's always interesting to see what companies are looking for. But I think that was enough of a tangent for now. So let's get back to the exercise. And it looks like we're onto the part where we're actually going to put in the configurations. So this is not the configuration for router E. I thought it was, but it looks like you're going to have us do that last. So I'll make sure that I've got the correct one up that I'm going to configure, and that's router A first. All right, so let's go ahead and doctor up this configuration so that it's ready to go. So for the most part, everything's going to be the same. We of course won't need any of this because we're not using frame relay. We're just going to see what happens when I just use a regular physical port, which is of course going to be GE000. So, and then we're going to try to just do everything the same. We're just going to use unit 0. Okay, so this is what we'll need, and I'm just going to type it all out. I can always set up both IPv4 and IPv6, but I think I'll just delete it and re-enter it. So I'm going to go edit interfaces 00.0. I'm going to delete everything under here, yes. And I'll set the description. I'll set the address. Oops, and oh, I've used a semicolon, not a colon. All right. So of course, if I were in production, I wouldn't be typing out these addresses like this. I'd be just copying and pasting them because that's a lot more reliable. But if I happen to make a typo, just more troubleshooting. So it's really kind of almost benefits to making typos in a lab environment because you get to have that troubleshooting experience. But there's obviously no benefits to making simple mistakes in a production environment. Oops, I'm gonna delete all this and then set routing options. Whoops. Oh, I'm already in that menu. Router ID 172. 16.1.1. So show pipe compare, commit and quit. And yep, we're getting rid of the IPv4 addressing, adding the IPv6 addressing. And let's do a commit check. Okay, and it succeeds. So if I do a run show configuration, you can see, oh, pipe display set. You see I still got that old configuration on there because I just checked the config to make sure I could use that keyword EUI-64 extended unique identifier without having to have all the frame relay stuff enabled. So let's go ahead and commit and quit. All right, and now it's time for the next device. It's going to be B. And I might just move fast on these. There's no sense in just watching me type out all of them. I mean, we really are going to be more interested in the Wireshark captures and the deep dives and the looking into the bits and the actual traffic being sent. Like me just typing things really isn't, I think, going to be very useful for the exam. Like, of course, I'm going to need to be able to enter things in quickly and accurately, but you know, even with that in mind, like I'm going to be doing more copy and pasting like this on the exam probably, because I get Notepad++, so I'll just be like pasting over things in Notepad++. All right, so router B is good to go. The other thing you can do, of course, is set up kind of a Python template where you can just, you know, enter in your variables or some sort of JSON form. You can fill out forms and stuff, but really, if it's doesn't provide an advantage over just copying and pasting in a text file, there's no reason to do it. I mean, one reason you can do that is if you've got a bunch of coworkers and they're all doing different things, you can kind of create a tool like that, and you know, the more time and effort you put into it, the more useful it's going to be, and eventually make a system that's much more useful than just copying and pasting into a notepad. And then once you do that, everything's, you know, the naming of the group, all that is going to be all standardized. Yeah, we can go into that in this channel. I mean, as I said, I want to kind of stick to the exam because that's what I am focusing on, but it's definitely important to know some level of programming skills, even if you're in a network engineering, especially more and more today, because it's just too useful. Like coding and stuff, it's just like, you know, how can you get by in society without being able to read and write? Well, how can you get by in a technical society without being able to program? It's kind of the same thing. Like you can, but it's not going to be as easy. You're going to be at a pretty big disadvantage. All right, so router C. Yeah, and one thing I'd recommend for anyone who wants to learn coding, just go to HackerRanks, Code Wars, some sort of site. I mean, you can even use Khan Academy, but it's not going to be tied into employers as much, because if you do those kind of challenges, especially on HackerRanks, they can actually, the employers can import your profile and tell right away if you're at the level of talent that they're looking for. So to spend an hour a day on that for a few months, year, multiple years, 2 hours a day, even a half an hour a day, after a while, you can have a really impressive profile on there. And if you're looking for a quick buck, just have employers start looking at that, and then you can get a job as a programmer without that much difficulty. So that's definitely, I would suggest to anybody, even somebody who's 3 years old, like open up an account, do that in your spare time, because you're going to have marketability, you're going to have the ability to make money and to be hired and to be valuable and to be valued if you have that record of the things you have done. Like, that's going to be very impressive and very useful to people who are willing to pay money to accomplish things. So yeah, I would definitely say even for like a 3-year-old, yeah, get them an account and see if they can work on some of those challenges. All right. And there's really no harm, as far as I know, in having an account and not having it be all that impressive. Like, you just, because it's like, yeah, you're just not at the level of coding that you need to be. Like, would you have even gotten a coding job if you didn't have an account like that? Like, it's not like you're gonna ever shoot yourself in the foot and say, hey, like, I'm actually really good at coding, I just have this account that says I'm bad. It's like, well, if you were really good at coding, what would the account say? So my account, I really don't spend a ton of time on it, but I think it is a kind of fair assessment of where I am, the kind of a advanced beginner, immediate level. But that, I mean, that even that level can get you far, because especially in like network engineering, you're entering a field where, like, this is the beginning of what is to come. So a lot of people in network engineering don't know any coding at all, and you're going to be talking about loops, and you're going to be talking about functions and very basic things. So if you know those things really well, and you've had some kind of project and you can show off a GitHub, you can say that you're a competent programmer, and you can do things that provide a lot of value, even without being a PhD, top of your class valedictorian, computer science graduate. Just a little bit of knowledge can go a long way. All right, so let's change this. Right, okay, so we're gonna need, oh, I'm still on router C. I wanna go on router E. Okay, and it seems to be starting with B for some reason, and A is at the bottom, so I'm gonna make sure that doesn't trip me up. I think I'm just gonna go straight to the command line. Configure private, edit interface 000.0, so that's gonna be to A, show pipe display set relative. Yep, 2A. So I'm going to delete the family INET for IPv4. Oops, I could just delete the whole family INET, so let me do that. There we go. So now I've got to set the address for IPv6, so I'll just copy paste that, save myself some time. Come on. Okay, now I'm going to go to the interface to router B, delete family INET, show pipe display set relative. Okay. All right, moving on. I can just up arrow all my commands I'm going to be reusing a lot. All right, so now it's time for the loopback interface. Okay, time to configure BGP. And I guess I'll just delete everything, make it easy on myself. And just go ahead and change this in the notepad. Change this to set. There we go, nice and easy. All right, so just two more things left. Oh, and looks like the router ID is not configured. But the autonomous system's right. So show pipe compare. And let's take a look at the Wireshark capture while it comes up. I have a feeling there's going to be a race condition. We'll see it try to initiate the BGP neighborship from both sides. But we can go back and add the passive command on there. Might be good just to see it happen again, just to kind of affirm that could be an issue. Oops, and it looks like there's a problem with it's starting the capture. Yep, so this is the classic kind of show-stopping error in GNS where it thinks it's already capturing, but no, it's not. So I'm gonna just commit this, and then I'm going to do another strategy that I learned yesterday and make a superfluous commit. Peer AS number must be configured for an external peer. So, and this is for neighbor 1DA. 1DA, let's see here. So 1DA, that's interesting. Why is 1DA? Now is this, where's 1DA. I don't see, there's 9DA, 5DA, 9DA, 15DA. So where's 1DA? Well, I think I'll leave it here, and I actually need to take a break. So in this video, we set up IPv6. We learned a lot about extended unique identifiers. We learned a lot about that, and I haven't seen the unpacked acronym. Well, I've really only seen the acronym, so it was really good for me to learn what it means unpacked. We learned how to build one of those for an IPv6 address, and we configured this lab, but unfortunately we've got a problem with that lab, so stay tuned for the next video where it's going to be more troubleshooting and figuring out what the problem is.